gentlemen, hope y'all are having an awesome day. Go concrete, beat asphalt. I'm Jon.
I'm David.
And we're here to talk to you today about the handheld penetrometer.
No, we're not.
Such a cool device. Love this thing.
Did that pop up again?
No, we're here. Sorry, I'm getting stuck over here. We're here to talk to you today about colloidal silica densifiers as it pertains to abrasion resistance.
Jon asks from YouTube.
And Jon is the owner of Valley Flooring Company for the last 16 years. Incredible dude.
Yeah.
Awesome guy. Thank you very much for sharing and asking questions.
Coming in from Oregon.
You are just, from Oregon. Here's the question. Ding!
What are some of the benefits of densifiers in relation to abrasion testing?
Okay.
Thanks, Patchouli. Well, I'm a stress strain guy.
I'm a stress strain guy. You're a stress strain guy.
I'm the stress strain guy, and data comes over to me to look at to see if cylinder A is better than cylinder B. And so we have a reference mix. We have a mix with the colloidal silica densifier, and every time penetration is less with the colloidal silica densifier and more with the reference. That says that the surface is harder, resist abrasion.
There was a paper that you and I started putting together a few years ago that went over the different things that helped increase the resistance to abrasive wear.
Right?
Whether it's underwater abrasion, steel wheel traffic abrasion, it all is based off of the same concept that some type of force at the surface is wearing away in a fatigue cycle sort of way.
Right.
That is happening over and over. And whatever the cycle is, whether it's close together, they're spread apart with breaks in between, but it's overcoming some certain things at the surface.
Right.
And then it goes into the subsurface, and if it's bad enough, it goes into the body of the concrete.
Right. There's the two tests we run here. There's the steel ball spinning test, which simulates heavy load traffic, as you suggested. It's for warehouses, pavements. It miniaturizes in the lab that type of situation.
And accelerates it.
And accelerates it, that's right. What we do in the lab is miniaturize and accelerate time. Then there's the other test you mentioned, the underwater test. It's exactly the opposite. It takes steel balls and spins them in water, so there's no actual surface pressure, but it has that tumbling, that pounding effect. It's like spillways, pipes, water treatment plants, those types of things. So once again, we bring a situation, a loading condition in the lab, miniaturize it, and accelerate time.
Okay. Now, when we look at how concrete responds to those abrasive forces, something that we like to talk about to start the conversation is that first line of defense.
Right.
Now, that's that hardened paste that's at the surface, that's covering up the aggregate and creating that closed surface to the layers that are underneath that top surface. Now, that hardened surface is the first thing those steel balls or rocks or simulation is going to tear away at. Now, we want to densify, harden, increase the integrity of that top surface as much as possible, because how well that top surface is doing dictates how well the rest of the test does.
Right. Dr. Belkowitz, would you distinguish between hardening and densification?
So hardening and densification at times can be related, but are not necessarily related. When we say hardening, we mean a certain type of strength.
Right.
Right now, you can build a microstructure that will have a definitive strength to it, or you can use a certain rock that has a certain hardness to it, which will relay strength to the entire concrete composite.
Right.
Now, that doesn't necessarily mean it's dense, and that doesn't necessarily mean that it will do well to abrasive forces, because what I was mentioning before about that paper that we were writing, which is, so I'm still looking for it. So it was a paper on abrasion resistance of concrete, and we recognize that there are three things that impacts the resistance to abrasion. One of the factors is the first line of defense.
Right.
When we look at most abrasion cycles, the denser you can make that top surface, that top 0.025 or less inches, the shorter, because you're going to sacrifice that first line of defense.
Right.
The more shallow you can make that loss over that given period of time, and that's normally within the first 3 50-second cycles out of 20 50-second cycles, or 24 50-second cycles. The shallower your slope is going to be for degradation, and the sooner you're going to reach a plateau.
So in that case, denser really means more solid.
Right, and that's the difference between hardness and denser.
Exactly.
A material doesn't necessarily have to be harder or stronger to be denser, but it normally is.
Agreed.
But what we're talking about is reducing the amount of pores,
Right.
pore structure, and pore connectivity,
Exactly.
and cracking at the surface, and that's our first factor.
Right.
Now, outside of that, denser also means having an impact not only on the body of the hydrated cement matrix of concrete, but also at that interfacial zone between the hydrated cement matrix and the aggregate.
Right.
So going on to the second factor, using colloidal silica, and there are a number of ways to use that, and we'll go into that here in a second. We're using up that calcium hydroxide in the pore water that's going to be within our pores and our connected pores to create more of the backbone of concrete strength, that calcium silicate hydrate, which gives us our hardness, and because we're closing up pores, we're also densifying as well as hardening.
Right. So it has more solid, and the solid is a better material.
Right.
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 The backbone, the CSH, is the stronger material. So we build more of that, which fills what might be otherwise be voids, makes it more solid,
Yep.
makes it more dense.
Right.
But it's also stronger.
Right.
So
right.
it's also harder. We're using stronger and harder, and we're using denser and more solid.
Amen. So that's the second factor. The third factor is that interfacial zone.
Right.
Once we get through that first line of defense into the subsurface of the concrete slab or pavement, and then into the body of it, it's not just about the strength of the paste, it's about the strength or bond of the aggregate into that hydrated cement matrix of our concrete composite.
Right.
Because if you have a very porous interfacial zone or a very weak interfacial zone, that abrasive wear can sometimes tear the aggregate out of your concrete composite.
Right.
So by using densifiers, we can enhance that interfacial zone.
Absolutely, and people are familiar with that. I mean, they see dusting on sidewalks,
Sure.
and in their driveways, they see some of that sand, come up or appear to come up to the surface. We're actually wearing away that top surface and wearing the sand, tearing the sand out.
And then eventually, a lot of sidewalks and a lot of residential driveways, not only do you start seeing the sand, but you start seeing, especially that rounded rock at the
Yeah.
surface, it starts getting exposed, and then rocks start to get yanked out. And on some surfaces, if you throw some rocks across it, you can actually hear a hollow sound where you have that shell that, all that freezing water is just pushing that stuff up.
Right.
Yeah. And that's the worst part. Once you get that top surface, abraded off, now you have the interfacial zone, which in my opinion is the weakest part of our concrete, because our interfacial zone is always going to be, or normally going to be, more porous than the body of our concrete. And what's his name? A.M. Neville, in Properties of Concrete on page 300 or 285, gives a wonderful description about it. I got it right over there on the wall effect and the surface area increase and how much more paste we need as we get closer to that interface, and that's why it's normally a more porous section of our concrete.
That plus on the stress strain side, I mean, if we've got that paste and we want to pull out a piece of aggregate, that's a tension strength.
Right.
Concrete doesn't have much tension strength.
Right.
So it's easy to pull or tear those particles out.
So we want to strengthen that zone as much as possible.
Right.
Going back to it, using colloidal silica is a great way of doing that.
Right. Every test we've run with colloidal silica on stress strain side has higher tension strength, has higher compression strength.
And it's not just that, David. I think it's you see a lot of manufacturers out there who have that data, whether it's the 779, it's the 943, the 1138, or some jabronis are using the Tabor test, which
Right.
if you're using the Tabor test, you're wrong. and you need to stop using it. It's not meant for concrete. It really is. I don't even think it's made for tiles. So stop using it. Stop putting it on your stinking brochure. Am I getting on a soapbox?
A little bit.
It's a dumb test. There are great tests out there. Don't use the Tabor test. But it was a good soapbox.
Yeah, you know, if you're in the rock business,
If you're in the rock business,
that's a different story.
that's a different story.
That's another day.
Anyway, so how to use densifiers. 3 ways. When you've got fresh concrete, best way of doing it, in my opinion, is mixing it in.
Put it in the truck.
Put it in the truck. You're going to get it throughout the body of the concrete. It's easy. It's already there on the job site. There's no, training of the finishing crew. Nothing for them to do because the technology is already there.
And it's usually under some type of quality control. The ready mix plants know how to use it. They've got data showing what that particular mix brand will do for you. So yeah, it's under good quality control usually.
The second method is by using a topical admixture, and there's a bunch of them out there that are either nanoparticle based or colloidal silica based, where you're using it to bring the surface back to life if it dries out, and then also has that secondary feature and benefit of densifying the surface to make the concrete more resistant to abrasive wears over time.
Yeah, as much as I hate to use the term, it does have a finishing. It is a finishing aid because it's liquid.
Right.
So any liquid helps finish. Not all liquids are good finishing aids because they weaken the surface.
Amen. And then the third method is after your concrete has hardened, this would be a retrofit, you come back and you spray colloidal silica over that surface that will then migrate into the concrete, create gels, and reduce the pore connectivity and the cracking that is created, which ultimately reduces the resistance to that abrasive wear.
It has to have something to energize.
Oh my gosh, totally.
It can't be something that's 100 years old and all the moisture's gone and
Sure.
Yeah.
Sure. So those are the 3 methods that we've seen that could be used. Using that colloidal silica technology to densify the concrete to reduce the impact of that concrete to the abrasive wear. I hope you learned something. If you have any questions based on this, please let us know. John, thank you again for that question. It was absolutely awesome. Don't forget to throw us those concrete questions, concrete concerns. Like and subscribe. Concrete note. Oh yeah, did you know we have a podcast?
Yeah, I knew that.
Yeah. Check out our podcast. It's pretty awesome. Yeah, we've got some great discussion. We read our articles for folks who don't have time to read them, and then we also have some commentary on them to give you more details and the plot holes that we've created. It's almost like Star Wars.
Yeah, we don't want you reading the articles while you're driving, but you can listen to the podcast while you're driving.
Unless you have a Tesla. Then you could totally. I think you could do that. I don't know. We don't have a Tesla.
Yeah,
we have a Dodge.
Yeah,
it's a great truck.
Could be an exception. Yeah.
Could be an exception. Thanks for joining us today. Have an awesome one. Go concrete.
Beat asphalt.